So, in lecture week 3 of this course on Newtonian mechanics with examples, we were discussing this problem of the suspension cable. So, in the previous lecture, we took a cable which is supported by both ends like this picture shown here, and in that case we assume that there is some external vertical load acting on the cable, but the cable itself is massless. Today we are taking another example in which we are going to assume that there is no external force apart from, but the cable is now massive. So, it has its weight, we cannot ignore the weight. So, the cable which is flexible is hanging under its own weight. So, let us define the problem. Again, these are two ends A and B, and the flexible uniform cable of length S. So, this total length from here to here is S, is suspended from two ends A and B, and it is hanging under the action of its own weight only. So, there are no other extra force. Mu is the mass per unit length of the cable. So, note the difference in the previous example that we took. In that case, the external load was W naught per unit horizontal length. In this case, the external load, the mass per unit length is per unit length of the cable. So, there is a crucial difference. Now, again the structure is in equilibrium, then what is the shape of this cable? Now, in the previous case we found, in the case of massless rope which is hanging because of some constant external load per unit length, the shape was a parabola. Let us see what we find in this case. So, let us recall that from the force from our analysis of by applying the condition of force balance, what we found is that, suppose this is my system, and let us kind of take a small piece. So, we took a small piece of the rope, and this small piece of the rope at this end is kind of changing. So, the tangent direction makes an angle theta plus d theta with the horizontal, and theta at one end and theta plus d theta at the other end, and the magnitude of the tension force is changing in this case because of the vertical forces. And now, we have some vertical force which is the weight. So, some vertical force, I am going to write it down. So, let us call that W, and this is the horizontal. So, this is the length of the rope, let us call that ds, and ds has two components, dx and dy. So, now what we found from horizontal force balance, we found our first equation, that the change in the horizontal component of the tension as we go from this end to the other end is 0. So, the horizontal component was constant, and the change in the, so this came from the horizontal force balance, and from the vertical force balance we got this constant, that the change in the vertical, the tension on the vertical direction was balanced by this external force. Now, in general, this W can be different at different point of the rope. In the previous example, we considered that W was constant. However, in this example, this W is the weight of the length of this slice of the rope. This is our system, which was the slice of the rope. Now, this W is times dx. So, that was the what we found. Now, in this case, this the weight, what is the weight of this slice of the rope? So, the per unit, so the mass is, the per unit length is mu, and the length of the rope is ds, of this our system is ds. So, this is the mass. If you multiply by the gravitational force, that is what will give us the W. the weight of this mass. Now, note that this ds is not same as dx, this is dx, this is ds. In fact, from geometry we have ds is dx square plus dy square. So, if I divide both sides, if we take a dx out, common out, then we get 1 plus the tangent. So, that means the vertical force is actually, so our vertical force, the weight of our system is mu times g times 1 plus dy dx whole square times dx. Now, this is our w, and because the curvature is changing at different point, continuously changing. So, dy dx whole square is not a constant. This represents the slope of this rope, which you can see from this picture, continuously changing, which means our effective load per unit horizontal length in this example is no longer a constant, but it is changing with x. How can we understand this? You can simply think of this way, that if I have the same amount of dx, the horizontal component, but at different, consider two pieces of rope which has same amount of dx, but one is, the angle makes with the horizontal is theta 1, and the other one is a little bit more bent towards upward direction. So, this is theta 2, theta 1 is, theta 2 is greater than theta 1. Now, if they have the same amount of dx, but the vertical elevation of this and this piece are different. So, the vertical elevation is more, which means to cover same amount of dx, you need this rope length of this piece with a slightly higher elevation must be longer, which means its mass must be longer, and hence its weight is also greater, and this is reflected by this factor, the slope is 1 plus dy by dx whole square. So, this is the effect of the mass of the rope. So, then in the previous example we got this equation. So, we had a third condition. So, we wanted to eliminate theta and replace theta by the y. So, we had this third condition, that dy dx is equal to tan theta, which is t sin theta, which is the t cos theta. So, this is the vertical component of tension, this is the horizontal component of tension, which, and this was a constant. So, some constant t and some ty, and if we take a second derivative, then we get which is, since that horizontal component is constant. So, we can take this out, then we get the derivative of the how the vertical component is changing with x, and this we have already calculated here from this equation. So, this is given by 1 by T naught times this W, and in this particular case we just determined what is W. So, we get W to be some mu times G divided by T naught times 1 plus dy dx whole square. So, our equation for curvature, which is the second derivative of the y as a function of x, in the presence of a, if the rope is massive, is now slightly different. It looks more complicated than the case where the rope is massless. So, and this effectively comes because the load, the vertical direction, the weight is load which is not constant per unit horizontal length, but this is constant. I mean, if the rope is uniform, then the mass density mu is constant. So, it is constant per unit length of the rope. So, this is what makes the difference. So, again to solve this equation, we need a boundary condition. And the boundary condition, as before, we will set that at origin, we will choose the origin at the middle, the lowest point of the rope. So, there y equal to 0 and dy dx equal to 0. Now, if we sort of how to solve this equation. So, let us assume that make a change of variable that dy dx is z, then I can write this as a first order differential equation. And I can do a variable separation. So, this mu g is something like w naught in the previous example. Now, this equation you can, I am not going to, I mean I am just assuming that you know how to do this integration. It is a standard indefinite integral. So, this will give you sine hyperbolic inverse and some constant of integration. Now, so that z is equal to sine hyperbolic some constant c prime. Now, if you apply this boundary condition that at x equal to 0 dy dx is 0, that is z is 0, then that gives this c prime equal to 0. So, then if you do one step integration, so we get dy dx is equal to sine hyperbolic mu g by t naught times x. So, let us go to a next line. So, z is equal to dy dx, which is equal to sine hyperbolic mu g by t naught x. Now, what is a sine hyperbolic curve? This is a quick recall here. So, we have this exponential function e to the power x and e to the power minus x. Then we can have two combination. One combination is called, if you take the difference, and the other combination is if you take the sum, average. So, these functions look very similar. So, you can check that they satisfy this identity cos hyperbolic x minus sine hyperbolic x is equal to 1. So, this looks similar to your famous trigonometric identity that cos square theta plus sine square theta equal to 1, with the difference that this is now a minus instead of plus. So, that is why we add this this cos and sine, and this also looks similar to a kind of equation of a hyperbola. This is related to the equation of a hyperbola. So, we add this hyperbolic. So, this is not a trigonometric function cos or sine, this is a hyperbolic function, hyperbolic cosine and hyperbolic sine. So, this is a different function. So, this is the definition for your reference. So, we are not going to use so much about. So, nowadays there are a lot of standard plotting tools available. So, you can, after this lecture, you can go back and use your favorite plotting software and plot this function and see how it looks like. So, one crucial difference, for example, with cos and sine function is that cos and sine function is a periodic function with some period 2 pi. It gets, its values get repeated after 2 pi, whereas this is not a periodic function. Now, if we integrate this further, and so we are going to use this identity that, so y is equal to sine hyperbolic mu g by t naught x dx. plus c, which is equal to cos hyperbolic mu g by T naught x plus c. So, this c 1 let us call it is another constant of integration. So, you can also check that if you calculate the derivative of cosine hyperbolic, you get e to the power x minus e to the power minus x by 2, which is equal to sine hyperbolic x. So, if you integrate sine hyperbolic back, you will get a cos hyperbolic, and there must be a constant. So, this is cos hyperbolic some constant time x. So, you get by chain rule you get this constant. Now, again at x equal to 0, if we assume that at x equal to 0 y is 0, then we can show that your C 1 is going to be 0. So, this is 0 from our boundary condition. So, now what is the value of C 1? So, note that C 1 has the dimension of the vertical height y. So, it represents some sort of height. So, we are going to choose that the C 1 to be 0, because this we can is basically sort of tells you the position, vertical position of the origin. So, this makes our life the equation simpler. So, you are going to choose C 1 to be 0. Then we get that this y x is equal to so this is the equation that determines the shape of a massive cable without any other extra load. So, the question is that this equation looks very different from the parabolic equation that we found for a massive massless cable, but let us see whether this is really different or not. So, here I show two functions. These functions are mentioned here. So, the one function represents this cos hyperbolic function, and the other functions represents the parabolic function. So, these are the functions are chosen so that it matches the equation that we found from our analysis. So, this will represents a massive rope or cable, and this will represent a massless rope or cable. Now, the question for you is that, but I don't tell you which function is this cos hyperbolic and which function is parabola. The point is that if you look at, so but here I am sort of showing you the plots, and if you look at the two curves, you will see up to quite for short distance away from your origin, that is the lowest point of the hanging cable. For small value of like distance away from the lowest point, these two curves are practically indistinguishable. It is only when you are going at a large length that these two shape of these two curves starts to differ. So, by the way, the shape of this curve, the cos hyperbolic curve, which represents the shape of a rope which is hanging under its own weight, is called a catenary. Now, so I will give you as a take home exercise to sort of plot these two functions in your favorite plotting tool, and then you determine which curve represents the massive rope and which curve represents the massless rope. So, the point is, for distance which is about more than certain, let us say 4 unit of length, then you will start to see that the shapes are not exactly same, but close to origin you can sort of assume that it is approximately a parabola. So, this is the reason for long time it was not recognized that the shape of a massive rope is in fact different from the shape of a massless rope. Now, we take a kind of some application oriented calculation. So, for example, a simple application could be that if you want to design a suspension bridge and here your material is usually the constraint. So, your length of the rope is given, then what will you choose as a distance between the two supports? Where are you going to choose this the distance between A and B? I will explain this picture. So, this is the again let us take this origin. So, then from here to one end, so this is called the span of the cable or span of the bridge, and then the vertical height of the support point. So, this represents the how much depression from the support the cable has. So, this is called the sag. Similarly, for the other end from here to here is your the span on the other end left hand end, and this is the sag on the left hand end. So, this if you add this distance which is LB and this distance LA, which gives you the total horizontal span of your bridge, let us say. And similarly, so now the question is that the length of the cable is given, then what will be the distance between A and B. So, in general, to answer this sort of question, what we require is to sort of know a relation between this span and the sag. And the other possibility could be that what is the material that you are going to choose for this suspension bridge, and for that you need to determine the tension that is there in along the length of the cable. So, here the problem will be to sort of know the tension. So, think of at each point. So, if this is the origin, this is x axis, y axis, each point has a coordinate x and y. So, determine the tension at this point. So, in this particular picture, I have taken a symmetrical hanging bridge. This is an asymmetrical hanging bridge, which is the more general case. This is symmetrical hanging bridge. So, LA is equal to LB and HA is equal to HB. So, I am not going to do a full analysis of this kind of problem, because that will take is not the focus of the physics. I am just sort of giving you the fundamental physical relation. So, you do not have to remember too much. You can start from first principles and then proceed with analysis in those cases. So, basically in this case what you want to know is that the relation between the suppose you take a small piece of the rope which has length, let us say ds. Now, it has a from one end to another end, the horizontal distance is dx and the vertical distance is dy, and then this will be the horizontal span. So, this will be called span of this small piece, and this will be called the sag of this small piece. So, you want to know the relation between span and sag. So, that is given by, for example, so we have this relation that from geometry we can write this from, and then if I take dx out, then I can write it as. So, this is the kind of mathematical relation between the span and sag of a small piece of rope. Now, if you integrate this, let us say from this end to this minimum, let us say from your origin to one end 0 to a, then you will get on the left and so integrate on both sides, and then it will go from 0. So, x grows from length grows from 0 to SA, then the length horizontal length grows from 0 to LA. So, this is the kind of the general relation. So, this will give you SA. So, this is the general relation that you get. So, now in the case you can do a further simplification. So, if you are in, like I will put it as a take home exercise. So, in the case of massless rope, in this case we derived that your dy dx was some simple function. Now, you can put it here and then assume that then you can expand this so that dy dx is less than 1. So, you can do a series expansion and then you get represent a relation with you can represent and see what happens. Now, I will quickly go through the other case. So, again it is basically similar exercise. So, Ty, that is the horizontal component, by Tx was your tan theta. So, now if we want to know the magnitude of tension at each point, so this will be given by our, remember our vector. So, it is a vector rule. So, it has two, this force has two components x and y, and again this is dy dx. So, this we have seen from geometry. So, if you take Tx out, you get Ty by Tx, which is again given by the same ratio 1 plus dy by dx whole square. Now, again if you, for the case of massless rope, this is a simple simpler function. So, which we derived in the previous couple of lectures. Now, I give you another exercise. So, now you, and T x was some constant. So, this was a constant. So, now you have this function. So, assume some value of T naught and you plot this function, plot this as a function of x. So, and determine where this function has this tension is the highest value. So, just from physical intuition, if you look at this picture, so you see that if you start from origin and go here, as you go towards right hand side, so tension at this point, for example, it has to support the weight of total length of this rope. Now, as you go and this point, it has to support the weight of total length from 0 origin to up to this part of the rope. So, you can expect that the tension must be highest at the end point. So, you can plot this and verify whether this expectation matches with your plot. Okay. So, thank you, and in the next few lectures we are going to take more interesting examples of the static condition. But before that, let me summarize like how we analyze this problem. So, we did it in 3 steps. First, you choose the system, which in our case, in this example, we choose a small piece of cable at the point x y. Then you identify all interactions acting on the system. So, this is where your Newton's laws of motions, third law and second law will come in handy. And then our third part is the analysis. So, in this case, the tool that we used was the force balance, and from applying this force balance, we got a differential equation for the local curvature, which means the second derivative of y as a function of x, the y present in the curve of the rope. And then we impose the boundary conditions. Is very crucial to solve this differential equation and determine the shape of the rope. And also we saw that this slope, the local slope of this rope, is important to determine the tension as well as to get a relation between the span and sag. So, this concludes our discussion on this suspension cable or suspension rope problem. So, we will take more examples in the next few lectures. Thank you.